Okay, A3. So this right here is an oxidation number problem. And so in this problem right here, you just go through and you look at the molecules and you figure out what the oxidation states are for the individual atoms that are part of it. Now, some of these are going to be a little bit more tricky because they may not follow exactly what you've expected from previous chemistry classes, but we'll talk our way through it, right? What the general approach and what the general rules should be in those cases. So going through A, right? So we have this bromite ion, right? So we have BrO3 minus in this case. And so an important thing to take into consideration here is that there's really a few things that are always going to be pretty strict in terms of what their oxidation state is. One of them is oxygen. Oxygen is almost always going to be a -2. It is incredibly rare for it to not have a -2 oxidation state. Solely because of, right, if you think back to what we had talked about during the periodic trends portion of the course, right, that's where it wants to be. And so in terms of figuring out these oxidation states, if you have an oxygen, you're in really good shape because it's just simply going to automatically be a -2. And then from that point, right, you can then easily figure out what the oxidation states are of everything else. Anytime, right, you have an element that's at the beginning of a molecular name or an ionic name, in this case right here, right, that should pretty much in every scenario always be a positively charged species. Sometimes you're going to have multiple ones, right? So like the H2SO4 or H2ASO4 minus in the bottom right corner, right? That can then kind of alter what's going on in those scenarios in terms of which ones, you have to kind of, think about it a little bit more. But, that's a pretty good rule to follow through. So if you have an oxygen, right, you're in really good shape. So in this first one right here, right, the oxygen, we're already going to simply assume that it has a 2- charge. And so then overall, right, you have 3 of them. And so that's going to give you a total of 6- charge total from those oxygens right there. Next, right, we have the bromine, right? And so now, right, the overall charge of this ion is only -1, and so that means then that you have to, balance everything out, and that bromine is going to have a positive charge. And so if the total charge of all the oxygens is 6-, and you only want to end up with a single 1- charge, then that means that the bromine has to have a 5+ charge in that case, right? Because that 5+, and then those 6-, and then those 3 2- charges, right, give you a total overall, ionic charge of a net charge of -1, right? And so that's how you approach that right there. So the bromine is going to have a 5+ oxidation state. Oxygen is going to have a 2-. And that's not unreasonable for bromine, right? If you look at the periodic table, that's just simply removing all of the p orbital electrons for it. And so it's not, an unreasonable oxidation state for bromine, but it can also have, different ones as well. But again, right, the biggest thing really driving what the oxidation number is really going to be the oxygen in this case. So now for B, right, looking at this right here again, we have oxygen here at the end. So that should tell us that the oxygen is going to be in the 2- oxidation state. And so that gives us an overall state of 8-, right, that you're going to be generating, right, because there's going to be 4 of them in this case. So that means then for the nitrogen, the only other atom that's present, it's, an overall neutral molecule. To balance that out and give you a neutral molecule, what you have to then have, right, is going to be then 2 4+ oxidation. Right? Let me put that right. 4 times that, right? So it's going to be 2 times that, right? And so if you want this to be 8+, right, yes, then it has to be 4+ for the nitrogen, which again isn't terribly unreasonable, right? There's 5 available in that case. But that gives you an idea of what the charge is, right? So all we're doing is simply balancing those out overall. Next, right, we have SF6. So the F, right, we would expect that to be the negatively charged species. So fluorine, right, based off of its position as a halide, should then have a -1 charge. In that case, right, so there's 6 of those. So we're going to have then a total of 6- charge. Overall, this is neutral, right? So we only have 1 sulfur. So in this case right here, right, to neutralize everything out, right, you're going to have 6+ right there. That means that it has to be 6+ in that case for the sulfur. right? And that's what that charge is right there. Again, our old friend oxygen is back again. So we have oxygen here. We already know that it's going to have a 2- charge, and there's 4 of these. So overall, the oxygens are going to be contributing an 8- charge. What we're trying to get to is a 2- overall charge right here. So that means then that we have to have a total 6+ charge then on our carbons. And so if we have our carbons right here, right, there's 2 of those. To get to that 6+, then, right, each carbon has to have a 3+ charge in that scenario. Next thing, right, we're looking at calcium hydride, right? So H2 now is at the end, and so that means that it's going to be negatively charged, right? The calcium is going to have a positive charge in those cases, which makes sense, right? Calcium, it's an alkaline earth metal, right? You wouldn't expect any of those to have any kind of negative charges, right? So those first 2 rows of the alkali and the alkaline earth metals, right? Those are always going to be positively charged. Very rarely do they deviate from their 1+ or their 2+ charges. Incredibly rare, especially for the earlier ones, the ones that are further up on the periodic table, right? So the easiest way that we can do this, right? So we have 1 calcium in this case, right? Based off of the position in the periodic table for calcium, we would expect that to be a 2+ charge in this case, right? So that means that we're going to have a 2+ there for that. That means that overall for the hydrogens, right, we're going to have a 2- charge because the total charge that we have is 0 in this scenario, right? So there's going to be 2 hydrogens, and so that means that each hydrogen has to have a 1- charge, which makes sense, right? Hydrogen can either have, gain an electron, right, to have a full, octet, right, to be completely fill its, 1s orbital in that case, right, and that gives you the 1- charge. Alternatively, right, the most common way that most people think about hydrogen, right, is that it gives up its electron and becomes H+. But in this scenario right here, right, it has an extra negative charge, right? And so it has, or an extra electron, sorry, to give it hydrogen. Last one, right? So H2ASO4-, right? We have 3 different elements in this case. And so one important thing to think about is that when you have hydrogens at the beginning of something, right, those are always going to be positive, right? Those are always going to be protons, essentially, right? They're always going to be positively charged 1+. Those are always going to be acids. And so if you have then a complex ion after it, so the ASO4-, that means then that the AS part, right, that first element there is also going to have a positive charge, right? Because again, on its own, right, you can have ASO4, and in this case, right, it would be 3- for this species right here, right? The H2 is just simply, acidic protons. And so going through that right there, right, we have our old friend oxygen, so we can just do our math that we want to right there for that. So it's 4 times the oxygens, and so each oxygen is equal to 2-, and so that gives us 8- here. We know then for the hydrogens, right, those are going to be positively charged. So we have 2 hydrogens for that. Those are going to be 1+, right? So that gives us 2+ for that. And then we have 1 arsenic in this case. And so then overall, the net charge is going to be 1- in this scenario. So to get to that 1-, what we need to have is that arsenic to have a 5+ charge then there, right? Because, 2+, 5+, that gives us 7+, 8- cancels out, you get 1- there. So that means that the arsenic then has to have a 5+ charge in that scenario. Yeah, and so then that's how you balance those, right? So the important things to think about, especially ones that have multiple atoms, is thinking about which ones are going to be positively charged, which ones are going to be negatively charged. There are some that will typically always be negatively charged, right? Oxygen is in most scenarios, very, very, very rarely would it have a positive charge. Right, but it almost always will be a 2- charge. That's the easiest way to approach that. For hydrogens, right, depending on where it is within the way it's written out, will then tell you whether it's going to be plus charged or minus charged. Same thing, right, with nitrogen and the halides and stuff like that, right? Those can always flip around and everything in those cases as well. But that's the easiest approach, I think, right, is first identifying which ones you can definitively identify, and then figure out what remaining charge is left, and then how does that distribute itself through the others in those scenarios. So yeah, so that's today's stream.